Why Mercury is liquid at room temperature. Mercury defies expectations for a metal. It exists as a liquid at standard temperatures. Unlike iron, aluminum, or steel, which remain solid, Mercury melts at a remarkably low -37, 9 degrees F -38, 8 degrees C. This unusual property isn't random. It's a consequence of the metal's atomic structure and the unexpected influence of relativistic effects, phenomena from Einstein's theory of relativity. The basics of metallic bonding: most metals bond through metallic bonding, where positively charged ions are held together by a sea of freely moving electrons. Stronger bonds mean higher melting points. The strength of these bonds depends on how readily atoms share electrons, and the periodic table trends generally predict that metals further down the table have weaker bonds due to larger atoms. However, Mercury's behavior breaks this pattern. The filled subshell anomaly: Mercury, a group 12 metal, theoretically has enough outer electrons to form strong metallic bonds. Yet these electrons occupy filled subshells, making them stable and reluctant to participate in bonding. This partially explains its low melting point, but the gap between prediction and reality remains vast. Extrapolating from established trends, Mercury should still be solid at room temperature, with a melting point around 266 degrees F, 130 degrees C. The role of relativity: the key to understanding Mercury's liquidity lies in relativistic effects. As you move down the periodic table to heavier elements, electrons orbit the nucleus at increasing speeds. Near the speed of light, these electrons no longer obey classical physics. Their behavior becomes governed by quantum mechanics. This results in surprising physical properties. Mercury, along with gold, experiences some of the most pronounced relativistic effects. The outer electrons contract towards the nucleus due to the strong attraction, shrinking the atom's effective size by around 20%. This contraction reduces the availability of electrons for metallic bonding, dramatically lowering the melting point. Lanthanide contraction and computational challenges: the effect is further amplified by lanthanide contraction, where filled electron shells poorly shield outer electrons from the nucleus, pulling them even closer. To model this accurately, scientists must use the complex Dirac equation instead of the simpler Schrödinger equation, which fails for high-speed particles. This makes simulations computationally intensive, but possible with modern computing power. The verified quantum explanation accurate simulations confirm that relativistic effects lower Mercury's melting point by over 360 degrees F, 200 degrees C. While periodic trends suggest a low melting point, relativity is what makes Mercury uniquely liquid at room temperature. Ultimately, Mercury's unusual state isn't a quirk, but a demonstration of how fundamental physics shapes the properties of matter at the atomic level.